Now we will try to formulate the orbital equation. So this is the Earth and this is the equatorial plane. This is the equatorial plane, and Earth is rotating around Z axis. This is the direction of the North Pole. Now, if satellite is revolving around the Earth with a radius of R, radius of that revolution or radius of the orbit is say R, then we can say the force acting on the satellite, that is the gravitational force acting on the satellite, is equal to mass into acceleration. So this is the basic foundation block or foundation idea of orbital equation, right? So from that we can get d2r dt square plus r by r cube into mu equal to 0. So this is basically a second order linear differential equation, and its solution involves 6 undetermined constant, and those 6 undetermined constants are called the orbital elements. So basically these orbital elements actually determines the characteristics of the orbit of a particular satellite. That means if we want to specify the location of a satellite in the sky, we have to know the 6 orbital elements for that particular orbit of that particular satellite. The orbit described by these orbital elements can be shown to lie in a plane and to have a constant angular momentum. The solution to this equation is difficult since the second derivative of r involves the second derivative of the unit vector r. Obviously, the situation will be difficult. To remove this dependence, a different set of coordinates can be chosen to describe the location of the satellite such that the unit vectors in the three axes are constant. Basically, these are the mathematical tools. So for that, what we do, we will change the coordinate system in such a way that the orbital plane of the satellite will be used as the reference plane. So satellite is revolving in this particular orbit, right? And we will assume this is the reference plane. This orbital plane will be the reference plane with three axes. This is the x0, this is y0, and normal to this plane as z0. So if we change the coordinate system, the new equation becomes this, and corresponding transformation equations are these. Okay. Now we will equate the vector components of r0 and phi0, and if we equate, we will get two equations. These are two equations, and using standard mathematical procedure, we are not going to the details of those procedures because these are the standard equations. So we will get the solution of the r0 equation as p by 1 plus e cos phi 0 minus theta 0. Okay, so situation is like this. This is the satellite, and this direction, that means towards us, this is the direction of the z0. This is x0 and this is y0. Okay, and this direction is the phi 0, and distance from the origin to the satellite is r0. So this is basically the equation of an ellipse with semilatus rectum p can be written in this way: h square by mu, where h is the magnitude of the orbital angular momentum of the satellite. Now this equation of the orbit is an ellipse, and it is the Kepler's first law of planetary motion. So we will discuss the Kepler's law afterwards. So we have proved that the equation of orbit for a satellite is elliptical one. Okay,